So we have a joint presentation up next from Beatrice Biasioli and Chiara Marcolla. And the title of the talk is Precision Tools for FHE Parameter Selection.
Thank you. So this is a joint work with Beatrice, Elena, and Sergi. So we divided the talk in two. In the first part, I will introduce our method, and in the second part, Beatrice will explain our tool. So why is it so complicated to find a good set of parameters for FHE? So all the FHE that we are using right now are based on learning with error problem or some algebraic variant. So I just want to recall the search version of this problem very fast. We have a system of integer equation perturbated by a small noise E, and what we want is find a secret vector S in ZQN. So to define this problem, we have to set 4 different parameters: the secret distribution S, the error distribution E, the modulus Q, and the dimension N. And when we set this parameter, by default, we also set in the security, because the security is a function of these 4 parameters, as we are going to see later. So why is it complicated to find these 4 parameters? So in the FHE scheme, we need the modulus Q big enough to allow a lot of homeomorphic operation. But when I increase Q, the security decreases. And so if I want to go back to the previous security level, I have to jump to the next n. And of course, because we use power of 2n, this jump is quite big. So the dimension increases a lot. And so the performance drops. So from one side, we need n and q very small for efficiency. To the other side, we want n and q very big for correctness or security. So right now, how we choose this set of parameters, at least a secure set of parameters, I guess everybody knows the lattice estimator by Albrecht, Player, Scott, is a super powerful tool where provide the running time of almost any LWE attack. So you can choose the secret and the error distribution, N and Q, and then the attacks that you want to know the running time. And it provides the running time, so the security. So the target parameter is the security. It's super flexible because you can choose whatever you want. But it's not easy to integrate with the existing FHE library, and sometimes it's also not fast. Starting from that, the homeomorphic encryption security standard decided to build some tables, so running the estimator and compute this table. So at the end, we have exactly the same parameter. And this work was updated last year in security guidelines for implementing homeomorphic encryption. Also in this case, for the pre-computed table, the target parameter is lambda, the security. But of course, because our table, you can choose actually all the parameters. You can find all the parameters. It's very fast and easy to integrate because our table, but is not flexible because our table. So what I want to introduce is our formula. Is a formula-based approach. We have formula for any parameter, and because our formula are flexible, easy to integrate, and also fast. Now we are going to see where this formula comes from, and to do so, I have to go a bit into theory, not too much. And so I have to go back to the LWE problem, because indeed the security of FHE scheme depends on the fact that we are not able to solve the LWE problem. And so the attack on FHE scheme are based on finding a good algorithm that solves the lattice problem. Here I just show some of the R problem or lattices. I not enter in detail because I have no time. So I just mentioned one of these that we are going to see later. That is the unique shortest vector problem. This problem asks to find a vector in the lattices that is one of the shortest one, knowing that is very, very small, much smaller than what we can expect. So which kind of attack we consider in our paper and in our tool are actually the primal BDD and USVP, because at the end of the day are the most efficient one. We also decided to add the hybrid attacks because sometimes often actually, outperform the other one, especially when the secret is sparse. And in the BGV-like scheme, they use sparse secret in general when there is the bootstrapping. And finally, we decided to not consider the dual attack because right now they not perform the others one. So how works this attack? The core part of the algorithm to solve the lattice problem is based on lattice reduction. So starting for a very bad basis, they wanted to find a good one with a shorter parameter and more orthogonal. And what we used to do so is BKZ beta algorithm. This algorithm takes a sublattice of dimension beta of our lattice and try to find the shortest vector in one of the shortest vector in this sublattice beta. So of course, the dimension of beta is super important because we cannot take neither too big or too small. So we have to determine the optimal beta for any attack. When we have the optimal beta, we can also find the running time of the BKZ beta algorithm because depend on beta and the dimension of lattice and this formula here. And so we have also the security. When we have the security, we can reverse the formula and find all the other parameters. So what we did, for any kind of attack that we consider, we find the optimal beta and so the other formula. But to do so, for the lower order term of the formula, we did some approximation. So because we wanted a very, very good formula for the FHE cases, we built a database starting from the lattice estimator. And then we fine-tune our formula with this database. Now we are going to see an example, the USVP. It's the same for BDD, for example. After that, we found the optimal beta, that is this formula here, that is quite heavy, poor formula. I don't enter in detail, but I want just to mention three things of this formula. One, that beta depends on all the parameters, as you can see, N, Q, sigma E, and sigma S. This formula is very good for any kind of LWE-based scheme. It's not just related on FHE, because it depends on the attacks. And this ugly formula, actually, is just the higher order term of the formula. So we decided to drop the lower order term, because it's already quite heavy, and then we compute lambda, as I mentioned before. So what we did then, for that reason, we wanted to build a database to fine-tune the lower order term. So this is the database that we built it. This is the range that we consider. Why we consider this range? Because for the BGV, BFE, KKS, in general, the secret distribution follows ternary distribution. Is a ternary distribution. Sometimes sparse, because, as I mentioned, when we use bootstrapping, or often we use a sparse secret. The error distribution is a Gaussian discrete with sigma E 3.19. And NNQ can really varies a lot in the range. And so that, the last one, is the number of points that we have in our database. Then we did the same for the binary secret distribution, because the GGGI-like scheme uses in general the secret distribution that is binary. For this scheme, N and Q are quite fixed. Indeed, N is 2 to the 10 or 2 to the 11. Q in general is 32 or 64-bit. But what is varies is sigma E. And what I want to point out here, that is in our database sigma E 3.19. But then Beatrice will explain how we have also the formula for the other sigma. Okay, after that, so what we did, we took our formula, we had some constants, ABC, in the previous one of security, and we fine-tune using couple optimization and finding the constant. After that, we decided to simplify more this formula because we really want to show the relationship between the parameter. So in this case, we can see that lambda is actually linearly dependent in N and in the inverse of logarithmic of Q. And we did exactly like before. So now I conclude my part. just to show how close our formula is with the lattice estimator result. In the graph there, in the plot, the points are the lattice estimator coming from our database, and the curve is actually our formula. And here I just show a table for the binary distribution. So the column with the estimator is the result, the outcomes of the estimator, the lattice estimator. The column with lambda is the result of our previous formula, and lambda S, the result of the second one, the simplified one. And as you can see, the result is really, really close, or actually exactly the same. Okay, now Bea, your turn.
So far, Chiara explained how we obtain formulas to compute the security parameter lambda from the theoretical analysis of the attacks. And in particular, this formula comes from two formulas. The first is to obtain the lattice reduction parameter beta. That is a formula that depends on all of the other parameters, so n, q, sigma e, and sigma s. And then this formula is plugged in the formula for the runtime of the attack to obtain the parameter lambda. Okay, what if instead we know the desired security for our scheme, and we want to compute another parameter, so for example, n or q? So we decided to reverse these formulas, and we obtain formulas to compute also the lattice dimension and the size of the modulus log q, and the standard deviation of the error sigma, the error distribution sigma e. Then we decided to do some optimization, and in particular, the reason is that we have some minor approximation. You can see what we were dealing with, so maybe understand. And when we were in reverting the formula, first of all, we have to revert the formula for lambda. And here we drop some non-leading terms, in particular the second one, which is still quite ugly. And this gives like minor approximation that are like not really noticeable, but we wanted some optimization anyways. So the first way to do that is with the fine-tuning phase and construction of the database that Chiara explained. In particular, we constructed a database for fixed sigma E 319, which is the standard choice of sigma E for BGV, BFV, and CKKS. But as Chiara explained, in CGGI, for example, we need more flexibility about sigma E. And so we are in the process of building some databases for the standard combinations of n and log q, and fine-tune our formulas also for these parameters. But in the meantime, we also have a second way to deal with these little approximations. And basically, we go one step back, and we consider again the system of equation given by beta and lambda. And instead of approximating lambda, we solve this system of equation using numerical methods. Numerical methods are mathematical tools designed to solve numerical problems. What are the pros of these two methods? Both are fast. The fine-tuned formulas one is numerical stable, easy to integrate in libraries, and shows very well how parameters relate in security. On the other side, the numerical methods do not require a database, which means that we don't have to stick to some values of the parameters, and allow parameters that have more complicated relations. So in particular, we use it also for the study of the hybrid attack. Okay, so we implemented everything, all of these in a tool, which is open source and in Python. How do we use it? For example, to estimate the parameter lambda, we can run estimate.py. We can choose as parameter lambda, and then we give our other parameters. In this case, we chose an example that could be some parameters for BGV or BFV and CKKS. So n is 2 to the 13, log q is around 200, and the secret distribution is ternary. Also, like the standard deviation of the error distribution is by default 319, but we will see how to change also that. And what I wanted to point out is that we can choose actually a range for log q. We don't have to put just one value. And the result will be a table that summarizes the parameter that we gave and outputs the security parameter lambda. Okay, we also implemented, just adding this dash v, we can see a comparison with the lattice estimators and with the lattice estimator, and as you can see, the results are pretty similar. Okay, so for now we saw an example of the secret distribution being ternary, but we can also set different distributions. So for example, here we can see the sparse distribution. We just put secret sparse and we specify the Hamming weight. In this example is 128. And in this case, since the most efficient attack is the hybrid attack, we will see the result, the security that comes from this one. Otherwise, we can choose the secret distribution to be binary. Here we chose an example that the parameters could come from CGGI. So we have n that is 2 to the 10, log q that can be either 32 or 64. The secret distribution is binary, and here we can change also the standard deviation of the error. And in particular, in the second example, we can see that we chose a much bigger value to obtain, for example, a security level that is around 80. Okay. Another thing that we can do is adding this dash table, which will show the security from the two attacks, and in particular from all of the formulas. Okay. Now, if instead we want to determine another parameter, so for example, here we want to determine n that gives a security that is at least 128. So we get as output the minimal n required, and also the closest power of 2, which is what is used in FHE in general. We give also examples for log q and sigma e. In particular, if we want to compute the parameter log q, we just use the log q, and we obtain the maximal value that for log q that we can use. And if instead we choose to define sigma e, we need to take a value that is at least the one showed. Okay, to conclude, what we achieved is to significantly accelerate the parameter selection, still maintaining flexibilities, and in particular, we propose a theoretical analysis of the most efficient lattice attacks on the LW problem. We obtain formulas to establish the relations among the parameters that are easy to integrate in libraries, and we propose an open source tool that implements our results. As a final remark, we would like to say that this analysis is not restricted to FHE, but it's valid for all the LWA-based schemes. Thank you for your attention.
Okay, thank you very much, Beatrice and Chiara. Any questions? Yeah, Yuri, go ahead.
Great talk. I have two quick questions. Hopefully they're very quick. The first one, it looks like the interpolations, the analytical interpolations that were obtained are, based on lattice estimator, based on a certain run of lattice estimator. Let's say the lattice estimator gets updated with some new attack is added, let's say for sparse secrets. How easy it is to update your tool so it would be up to date with lattice estimator?
Sì. So if there is a new attack, we have, of course, to study the formula for the new attack. So we have to do the math behind, study the attack, and then update it is not so difficult, I mean. We have just to study, write the formula, and run the estimator and fine-tune for that one. So, of course, we have to study the new formula coming from the new attack. Yes, this for sure.
Maybe just a second quick question. One of the current practical limitations that I see from the lattice estimator is when we try to generate parameters for large ring dimensions, like 2 to the power 16, 2 to the power 17. How good is your tool for those, or maybe does it use extrapolation or something? Because this is a problem, practical problem that I've run into.
They are very good, are very close to the one of lattice estimator. Because the point is that in that case, it's very complicated, it's very long to get the result from the lattice estimator, right? With n is so big. In this case, we also check some, just to check, and was very good. Even if the interpolation go from 2 to the 10 to 2 to the 15, we saw that actually follow really nicely also for the other bigger power of n.
And there is no restriction, right, on the upper bound. Let's say 2 to the power 17, 2 to the power 18 would still work.
Yes. Yeah.
It would be useful to have graphs, just to show. What I mean by that is, well, 3.19, whatever the standard things for things, a graph of log Q versus security, for example. The point being, we all believe, at least with the current state of the art, that lattice reduction is fully exponential, and the only thing we care about is the constant in the exponent, and a graph would show you that, well, the constant in the exponent is 1 over 40, or 1 over 50, or whatever it is.
Yeah. Sorry, was not a question, right? Okay. Because actually, no, true, but this formula here is actually, this part here is actually what you mentioned. Yeah, see. We just fine-tune the lower order term at the end of the day.
Okay. Any more questions? I could do a quick one. When you do your approximation, do you take into account, or do you try to kind of stop being, which way around, above the lattice estimator values?
No.
Do you consider, okay, so it's just
no. Yes, we try to almost always, so I try to push to be behind the security, to almost never overestimate, the security. So, yeah.
Okay.
Almost that I was.
Cool. All right, well, if there's no more questions, let's thank the speakers again.